In chem activity number 14, we'll be looking at the concept of half-lives. This is an extension of looking at the integrated rate laws as a means of studying kinetics. In particular, we'll be looking at what happens for half-lives for first-order reactions. We'll be looking at what happens for half-lives for 0 and second order in the second video. So we'll start with the decomposition of chloroethane, which you're told right at the top here is a first-order reaction. Now you can see a graph for this particular decomposition where the concentration of chloroethane is in the y-axis and the time is in the x-axis, and I'm hoping from the shape of the graph that you would already suspect that it may be a first order reaction. Just to recap some of the things that we saw for integrated rate law graphs is if we monitor the concentration of A, so A let's say representing some chemical like chloroethane as a function of time, and if you get a straight line, well then you know that you're dealing with a zero order reaction. However, if you monitor the concentration of A, some reactant, as a function of time, and if you get a curved line such as this, and similar to the graph that's actually shown on this page, then you suspect that you either have a first order reaction or a second order. And so you'd need additional information to distinguish between these two. In this particular case, of course, we have a first order reaction. Okay, so looking at this graph a little more carefully, you will start to see the point that I'm going to be trying to illustrate related to half-lives. The idea is that I'd like you to notice the time it takes for the concentration starting at 0.20 to go down to 1/2 of its original value. So that would be 0.10. Now I've tried to, in a sense, mark up the graph fairly extensively so that you can indeed see these relative points. And I hope you can see that the time it takes for the concentration to drop from its original value down to 1/2 is indeed 7 seconds. And we can kind of mark it right here like this. And you can see that what's happened is the concentration of the chloroethane has gone down by 1/2. And what we'll do is we'll call this first period of time the first half-life. And the first half-life is 7 seconds. Now, just in case you're wondering about this definition of half-life, if we just scroll down a little bit, you'll see the definition written right here. The half-life for a reaction is the time. So note, it's actually a time. It's not a change in concentration, but rather we'll have the units of minutes and seconds and hours. It's the time it takes for the concentration of a single reactant to reach 1/2 of its original value. So that in itself is fairly straightforward. But one of the interesting things about reactions is that we can have successive half-lives. So what we just saw here is the first half-life, in that the original concentration was 0.20 molar, and then we go down to 0.10 molar. Well, if we now start at 0.10 molar and we go down to 0.05 molar, we're actually now looking at the next half-life. And you can see over the course of this period of time, the concentration of A, if you start at 0.1 molar, has gone down by 1/2. And so we would refer to this as the second half-life. And the second half-life, if you look carefully, starting at 7 seconds and going to 14 seconds, is once again 7 seconds. And we can even look at a third half-life, going from 0.05 molar down to 0.025 molar. So that would be represented by this portion of the graph. So once again, the concentration of A went down by 1/2 of its original amount. There's the original amount now being 0.05 molar, and we would refer to this as the third half-life. And this third half-life would once again be 7 seconds. So I'm hoping that I've convinced you that indeed the half-life for this first order reaction is a constant. And I'm going to make that point right here. Okay, in asterisk we can say for a first order reaction, and I'm going to add only, because as we will see when we study 0 and second order, this will not be true. So for the first order reaction time 1/2 is equal to a constant. And in a minute, we'll see an equation that represents this. But I first of all would like you to get this point, that indeed it's a constant. And this is going to be very helpful to us. To convince you further, though, how about we take a different time sequence and concentration halving. And so I'm going to start with 0.15 molar. Right? And as you know, half the concentration of 0.15 molar would be 0.075 molar, so it'd be down to here. Okay, so in blue, starting at 0.15 molar and going down to 0.075 molar. The initial time is roughly 3 seconds. So I know I'm not using a ruler here, but I think you'll agree with me that at 0.15 molar, this is the concentration at about 3 seconds. The time at which the concentration is now 0.075 molar is pretty close to 10 seconds. And of course, the change in time to go from 0.15 molar down to 0.075 molar is, hopefully no surprise to you, 7 seconds. So it doesn't matter where you set your initial concentration. As long as you allow the concentration to drop by 1/2, it will give a particular time. Now note, this is a time for this particular reaction at a particular temperature. So the half-life will always be a constant, but of course it depends on the type of reaction. It also depends on the temperature. If it's a first-order reaction, though, it will be a constant. Now, you may have heard of this idea of half-lives before, and it might have been in the context of radioactive decay. And as it turns out, many radioisotopes decay according to a first-order reaction. And this is very helpful because if you know the half-life for a particular isotope and you're able to measure its quantity at a particular time, it allows you to estimate how long it took for that radioisotope to decompose, and therefore you're able to predict when the original isotope existed, and therefore get a sense of dating when the original rock was around, or that sort of thing. Okay, so this allows you to do a radioactive dating. Okay, now I'd like for us to look at the equation that describes the half-life for a first-order reaction. So I'm going to use a very generic setting. So for a first-order reaction, starting with A here and going to products, okay, so very simple, A disappearing. And I'm going to start with our first order integrated rate law of the form of natural logarithm concentration of A at a particular time divided by the original concentration equals negative KT. And of course we can find this equation or one that's related to it on our formula sheet. And to add to this, we'll just indicate that we'll look at the concentration of A when it reaches 1/2 of the original concentration. And so what I'll do is I'll take my integrated rate law and I'm going to substitute in what would be the concentration of A at 1/2 of the original concentration. And so putting this in here, so concentration of A at a particular time is now going to be 1/2 the original concentration, all divided by the original concentration is equal to negative KT. So as you might imagine, the original concentrations now cancel, and this will leave me with ln 1/2 is equal to negative KT. Logarithm rules allow me to multiply both sides by a negative sign. This will result in ln 2 on the left-hand side. And then, of course, multiplying the right-hand side by a negative sign will result in a positive KT. So therefore, we'll have ln 2 is equal to KT. Of course, ln 2 is equal to 0.693. Note the time in this particular case, because I chose to use a concentration 1/2 of the original concentration, is indeed the half-life time. So I'm going to fill this in here, rearrange, and solve for the half-life. And so the half-life will equal ln of 2 divided by K, or as indicated in this equation over here, 0.693 divided by K. And so you'll find this half-life equation on your formula sheet, so you have it readily accessible. But you can see that there's nothing that the half-life depends on in terms of concentration. It's 0.693 divided by whatever the rate constant is. And of course, the only thing the rate constant depends on is temperature, other than the nature of the particular reaction. Now, over the past couple of lessons, we've been seeing various ways that we can determine the rate constant. We can determine it from the initial rate method equation, the rate law. We can determine it using some of these integrated rate laws. And I'm hoping you can see now, if you have a half-life, you can also determine your rate constant. And so I'm going to take this newly derived equation and say, well, K is equal to 0.693 divided by the half-life. And for the reaction that we've just been studying, the decomposition of the chloroethane, we know the half-life is 7 seconds. So I can go 0.693 divided by the 7 seconds. And so doing the math here, it comes to 0.099, and you can see the units are seconds to the -1, which is a perfect set of units for a first order reaction. This is probably the easiest way to find the rate constant if you happen to be able to pick out what the half-life is for an equation. So in the next activity, we'll introduce, pardon me, not the next activity, but the next video for the same activity, we'll introduce the equations for the 0 order and for the 2nd order, and show you how, by looking at successive half-lives, you can actually make a prediction about the order of the reaction. And of course, you can always solve for the rate constant.